Let us now consider bonding in molecules and treat the case of the simplest molecule, that is H2 plus, consisting of 2 hydrogen nuclei and a single electron. Since there is only one electron, there is no interelectronic repulsion term, and the Hamiltonian consists of the kinetic energy of the single electron and potential terms for the attraction of that electron to the two nuclei. Hund, Mulliken and Jones developed the molecular orbital theory between 1927 and 1929 by taking linear combinations of atomic orbitals to form the molecular orbital psi. So the molecular orbital psi is formed by a linear combination of the atomic orbitals phi I. Why can we do this? Well, recall that the eigenfunctions of a Hermitian operator form a complete set of functions which can be used to expand any other function. Therefore, the Hamiltonian for the hydrogen atom is a Hermitian operator, as we have already seen, and its eigenfunctions are the 1s, 2s, 2p, etc. atomic orbitals. So these atomic orbitals, which are eigenfunctions of a Hermitian operator, can be used to expand the wave function for H2 plus. Okay. The simplest approximation is the LCAO-MO approximation with a minimal basis set, that is a basis set consisting of only the 1s orbitals on the two atoms. So psi equals Ca 1sa plus Cb 1sb. Therefore, psi squared is equal to Ca squared 1sa squared plus Cb squared 1sb squared plus 2Ca Cb 1sa 1sb. Since the two nuclei are identical, the probability of finding the electron around nucleus A has to be the same as that of finding it around nucleus B. Therefore, Ca squared is equal to Cb squared. There are only two possibilities. So either Ca is equal to Cb, which leads to the bonding molecular orbital 1sa plus 1sb, or Ca is equal to minus Cb, which leads to the anti-bonding molecular orbital 1sa minus 1sb. The bonding molecular orbital is called the Gerade molecular orbital, since it is symmetric to inversion, and the anti-bonding molecular orbital is called ungerade, since it is antisymmetric to inversion. Ng and Nu are the normalization constants. So here we see the Gerade molecular orbital 1sa plus 1sb, and here we see the ungerade molecular orbital 1sa minus 1sb. Okay. The Gerade molecular orbital is formed by constructive overlap of the 1sa and 1sb orbital, whereas the antibonding molecular orbital is formed by destructive overlap of the 1sa and 1sb atomic orbitals. Recall that if psi 1s is an eigenfunction of the Hamiltonian for the hydrogen atom, then its negative minus psi 1s is also an eigenfunction with the same eigenvalue. We will use this. To evaluate the normalization constants, we expand bra psi g ket and bra psi u ket, and if we assume that the atomic orbitals, the 1s atomic orbitals are normalized with overlap integral s equals bra 1sa 1sb ket, then the normalization of the molecular orbitals requires that Ng is equal to 1 upon root of 2 plus 2s and Nu is equal to 1 upon root of 2 minus 2s. And since 1sa equals 1 upon root pi e to the power minus ra, and 1sb equals 1 upon root pi e to the power minus rb, it can be shown that s is equal to e to the power minus r into 1 plus r squared by 3. We can now evaluate the electronic energies by taking the expectation value of the electronic Hamiltonian. Thus, Eg equals bra psi g He psi g ket, which is equal to 1 upon 2 plus 2s, bra 1sa plus 1sb, He 1sa plus 1sb ket, which is equal to 1 upon 1 plus s, Haa plus Hab, where Haa is the diagonal element, is the diagonal matrix element of the electronic Hamiltonian between the atomic orbital bases, and that is Haa equal to bra 1sa He 1sa ket, and Hab equals bra 1sa He 1sb ket is the off-diagonal matrix element of the electronic Hamiltonian between the atomic orbital bases. Likewise, Eu equal to bra psi u He psi u ket, which is equal to 1 upon 2 minus 2s, bra 1sa minus 1sb, He 1sa minus 1sb ket, which is equal to 1 upon 1 minus s, Haa minus Hab. We can then construct the molecular orbital energy level diagram as shown here. And as we have derived, Eg equals Haa plus Hab by 1 plus s, and Eu equals Haa minus Hab by 1 minus s. Since Hab is negative, so the bonding or Gerade molecular orbital is lower in energy than the atomic orbitals, and the antibonding molecular orbital is higher in energy than the atomic orbitals. We then include the interelectronic repulsion to get the potential energy curve. But since minus half del squared minus 1 upon Ra is the Hamiltonian for hydrogen atom A, and minus half del squared minus 1 upon Rb is the Hamiltonian for hydrogen atom B, that means this is equal to EH 1sa, and this is equal to EH 1sb, where EH is the energy of the 1s atomic orbital. So we get Eg plus 1 upon R equals EH plus 1 upon R plus epsilon A plus epsilon AB by 1 plus S, and Eu plus 1 upon R equals EH plus 1 upon R plus epsilon A minus epsilon AB by 1 minus S, where epsilon AA and epsilon AB are the diagonal and off-diagonal matrix elements of the atomic potential energy term. I will not go through the detailed derivation, but if you want, it is outlined here on this slide. So with that, the binding energy that we obtain for H2 plus from LCAO-MO theory with a minimal basis set turns out to be only about 60% of the experimental value. This is the experimental potential energy curve. This is the potential energy curve we get with the bonding molecular orbital Eg, and this is the potential energy curve that we get with the antibonding molecular orbital. So we see that the Eg energy is only about 60% of the total binding energy. Okay. We can now consider the case of the neutral hydrogen molecule with molecular orbital theory. The LCAO molecular orbitals stay the same as before, but now since hydrogen has 2 electrons, since the hydrogen molecule has 2 electrons, we construct the ground state wave function by putting both electrons in the lower energy or bonding molecular orbital, one with alpha spin and the other with beta spin. But we have to make this wave function antisymmetric with respect to interchange of electron labels as required for fermions. As we have seen, the arrangement with electron 1 having alpha spin and electron 2 having beta spin, and that with electron 2 having alpha spin and electron 1 having beta spin are indistinguishable, and we have to form the antisymmetric ground state wave function for H2 by taking the antisymmetric linear combination of these two arrangements, that is psi equal to 1 upon square root of 2 sigma g alpha 1 sigma g beta 2 minus sigma g alpha 2 sigma g beta 1. This antisymmetric 2 electron wave function is conveniently written in the form of a Slater determinant. That is psi equals 1 upon root 2, the determinant of psi g alpha 1, psi g beta 2, psi g alpha 2, psi g beta 2. Let us now treat the hydrogen molecule using valence bond theory, which was developed by Hitler and London in 1927, based on the observation that the electronic structure of atoms is largely preserved in a molecule, as we can see if we look at the X-ray diffraction pattern of a molecule or a crystal. The energy of the covalent bond is then associated with the exchange of electrons between atoms. So the wave function for the electron pair bond between atom A and atom B is given by psi plus minus for the symmetric and antisymmetric wave functions is given by the normalization constant times 1 is A1, 1 is B2, plus or minus 1 is A2, 1 is B1, with S being the overlap integral between the atomic orbital wave functions. Then the Hamiltonian, the electronic Hamiltonian is given by minus half del 1 squared minus half del 2 squared, the kinetic energy terms for the two electrons, minus 1 upon R1a minus 1 upon R1b minus 1 upon R2a minus 1 upon R2b for the potential energy of attraction between electrons 1 and 2 and the nuclei A and B, plus 1 upon R12, the potential energy of interelectronic repulsion. We can separate out this electronic Hamiltonian into HA, with this Hamiltonian for hydrogen atom A, plus HB, the Hamiltonian for hydrogen atom B, plus H dash, the interaction Hamiltonian. And this gives E plus the energy for this symmetric combination equal to 2EH plus Q plus A by 1 plus A squared, and E minus the energy for the antisymmetric combination is equal to 2EH plus Q minus A by 1 minus A squared, where EH is the energy of the hydrogen atom, Q is the integral bra 1s A1, 1s B2, H dash 1s A1, 1s B2 ket, and A is the integral bra 1s A1, 1s B2, H dash 1s B1, 1s A2 ket. Okay. We can then evaluate the integral Q, and you can go through the derivation, which basically consists of straightforward algebra. The expression we obtained for the energy was E plus minus equals 2EH plus Q plus minus A by 1 plus minus S squared, where Q is equal to minus integral rho A1 by R1b theta 1, the classical Coulomb attraction of the electron density around atom A to nucleus B, minus integral rho B2 by R2a, the classical Coulomb attraction of electron density around atom B to nucleus A, plus the double integral rho A1 rho B2 by R12 theta 1 theta 2, the classical Coulomb repulsion of the electron densities of electrons 1 and 2, plus 1 upon capital R, the classical Coulomb repulsion between the two nuclei. The integral A has no classical analog. Okay? So we saw that Q is just a sum of classical Coulomb terms, whereas the integral A has no classical analog, okay, and it arises because of the antisymmetry requirement between the two electrons. And this, the lower energy state, psi plus, gives a binding energy of only about 60% of the observed value for hydrogen. Again, I will not go through the derivation in detail, but you can go through it if you are interested. Because of the antisymmetry requirement for fermions, the symmetric combination of the orbitals, that is psi plus, has to be combined with an antisymmetric spin function to yield an antisymmetric total wave function for the singlet state. Thus we write singlet psi plus equals normalization constant times 1s A1, 1s B2 plus 1s A2, 1s B1 times 1 upon square root of 2 alpha 1 beta 2 minus alpha 2 beta 1. And this can be written as a combination of two Slater determinants as shown here. Or we can combine the antisymmetric combination of the orbitals, that is 1s A1, 1s B2 minus 1s A2, 1s B1 with a symmetric spin function to yield a total antisymmetric wave function for the triplet state. Thus, triplet psi minus equals normalization constant into 1s A1, 1s B2 minus 1s A2, 1s B1 times either of these three symmetric spin functions, that is alpha 1 alpha 2 or 1 upon root 2 alpha 1 beta 2 plus alpha 2 beta 1 or beta 1 beta 2. So there are three components of the triplet state. So to summarize, the wave function for the singlet state, that is s equal to 0, ms equal to 0, 2s plus 1 equal to 1, is given by the combination of the symmetric combination of the orbitals with the antisymmetric combination of the spins. Whereas the triplet state, s equal to 1 to 2s plus 1 equal to 3, is given by the antisymmetric combination of the orbitals with one of the three symmetric combination of the spins, alpha 1 alpha 2 for ms equal to 1, alpha 1 beta 2 plus alpha 2 beta 1 for ms equal to 0, and beta 1 beta 2 for ms equal to minus 1. Before we conclude, let us compare the molecular orbital and valence bond wave functions. In molecular orbital theory, we first form one electron functions, that is molecular orbitals, by a linear combination of atomic orbitals procedure. Thus the molecular orbital phi is given by the normalization constant times 1sa plus or minus 1sb for the bonding or anti-bonding orbitals. And then we put the electrons into these molecular orbitals to get an antisymmetrized Slater determinant wave function. Thus, the molecular orbital wave function for the two electron system is square root of half times the Slater determinant phi alpha 1, phi beta 1, phi alpha 2, phi beta 2, which is also written concisely in this form. In valence bond theory, on the other hand, we form electron pair bonds between atoms to give an antisymmetric singlet wave function, which can be written as a linear combination of two Slater determinants. Thus, the molecular orbital wave function for the two electron system formed by putting both electrons into the bonding or Gerade molecular orbital and then expanding that molecular orbital using the linear combination of atomic orbitals procedure gives us n squared times determinant 1sa plus 1sb alpha times 1sa plus 1sb beta. And if we expand this out, we see that it's a sum of four Slater determinants, that is n squared times determinant 1s a alpha 1s b beta plus determinant 1s b alpha 1s a beta plus determinant 1 as A alpha, 1 as A beta, plus determinant 1 as B alpha, 1 as B beta. We see that this is a 50-50 mixture of the valence bond, covalent and ionic wave functions. We have already seen the valence bond covalent wave function, which is the normalization constant times the determinant 1 as A alpha, 1 as B beta, minus the determinant 1 as A beta, 1 as B alpha. The first determinant corresponds to the alpha electron on atom A and the beta electron on atom B. The second determinant corresponds to the beta electron on atom A and the alpha electron on atom B. These are covalent wave functions. The ionic wave function is given by the normalization constant times the determinant 1 as A alpha, 1 as A beta, plus the determinant 1 as B beta, 1 as B alpha. The first determinant corresponds to both the electrons on atom A, and the second determinant corresponds to both the electrons on atom B. Thus, the first determinant corresponds to A minus B plus, and the second determinant corresponds to A plus B minus. And these are therefore both ionic wave functions. This mixing of covalent and ionic configurations is an instance of configuration interaction, which we will study in more detail later. So let us see how these methods perform. The Heitler-London wave function gives us a dissociation energy of 3.14 electron volts, significantly underestimating the value, since the experimental dissociation energy is 4.7466 electron volts. And the Heitler-London wave function overestimates the equilibrium bond length as 0.87 angstroms compared to the experimental value of 0.741 angstroms. The LCAO-MO wave function does even worse. While it also overestimates the equilibrium bond length, it gives us a dissociation energy of only 2.65 electron volts. And this is understandable because the LCAO-MO wave function, as we saw, gives us a 50-50 mixture of covalent and ionic structures, whereas for the homonuclear hydrogen molecule, we expect that the covalent structure should be the major contributor, and we should expect a relatively small contribution from the ionic structure. Therefore, if we mix in the covalent and ionic structures, but allow the percentage of ionic structure to be that we mix in to be determined by the variational theorem, then we get a significant improvement in the dissociation energy to 3.23 electron volts. If we further allow the exponent of the Slater function, that is e to the power minus zeta r, in hydrogen the zeta is just equal to 1. But if we allow that zeta also to vary and be determined by the variational theorem, we get a much better improvement, and the dissociation energy is 4.02 electron volts compared to 4.7466 experimental, and the equilibrium bond length is also much better, 0.748 angstroms compared to the experimental 0.741 angstroms. Okay. The other methods, if we use the Hartree-Fock self-consistent field procedure, we get 3.72 electron volts dissociation energy and 0.74 74 angstroms equilibrium bond length. Using configuration interaction on the Hartree-Fock self-consistent field Slater determinant, we get a dissociation energy of 4.71 electron volts, much better, and an equilibrium bond length of 0.74 angstroms, which is within the experimental error. And the best wave function obtained so far by Kolos and Rothan using a 50-term expansion gave 4.7467 electron volts dissociation energy, well within the experimental error, and 0.74 angstroms equilibrium bond length. Okay, so this is just to show that the quantum mechanics can give us as accurate results for these small systems as we can hope for. In the next episode, we will go beyond the Born-Oppenheimer approximation.